What if everything we think we know about the universe's expansion is wrong? Picture this. For decades, scientists have believed the cosmos is stretching apart at a steady, predictable rate, a fundamental idea that shapes our understanding of everything from the birth of galaxies to the very fate of reality itself. But what if that rate isn't steady at all? What if the numbers don't add up, and the universe is hiding a secret so big it could rewrite the textbooks? This isn't science fiction, it's called the Hubble Tension, and it's one of the most baffling mysteries in modern cosmology. Here's the problem. When we measure how fast the universe is expanding using nearby stars and galaxies, we get one number. But when we look at the faint glow of the Big Bang itself, the cosmic microwave background, we get a completely different answer. These two methods, both trusted and tested, disagree by just enough to throw everything into question. It's like checking two clocks that should be perfectly synchronized, only to find one is ticking faster than the other. The difference might seem small, but in the grand scheme of the cosmos, it's a gaping hole in our understanding. Could there be something fundamental we've missed, a hidden force, a flaw in our theories, or is the universe playing a trick on us? This isn't just a technical debate for scientists in lab coats. It's a cosmic detective story that challenges everything we thought we knew. If the Hubble tension is real, it means our universe might be evolving in ways we never anticipated. Maybe dark energy isn't what we thought. Maybe gravity behaves differently on cosmic scales. Or maybe, just maybe, there's a whole new chapter of physics waiting to be discovered. Strap in, because we're about to dive deep into one of the most thrilling puzzles in science, and by the end, you might never look at the night sky the same way again. The Hubble tension is more than just a scientific discrepancy, it's a cosmic paradox that's shaking the foundations of modern cosmology. At its core, it's the stubborn mismatch between two ways of measuring how fast the universe is expanding. On one hand, we have local measurements using celestial landmarks like Cepheid variable stars that pulse with a rhythm so precise. They're like cosmic lighthouses helping us gauge distances. When we calculate the expansion rate, or Hubble constant, using these nearby objects, we land on a specific number, but here's where things get weird. When we turn our gaze to the afterglow of the Big Bang, the cosmic microwave background, or CMB, a snapshot of the infant universe, the math predicts a different expansion rate entirely. This isn't a small, rounding error. The gap between these two numbers is big enough to keep cosmologists up at night. If our local measurements are correct, the universe should be expanding about 9% faster than what the CMB data suggests. That might not sound like much, but in the grand equations governing the cosmos, it's a glaring inconsistency. Imagine baking a cake using the same recipe for decades, only to suddenly realize the oven temperature you've relied on this whole time is off by just enough to ruin every batch. The recipe, our standard model of cosmology, might need a tweak, and no one's quite sure where the mistake lies. What makes this tension so disruptive is that both methods are incredibly reliable. Cepheids and supernovae act as cosmic yardsticks, meticulously calibrated over a century of observation. Meanwhile, the CMB is like a time capsule from the universe's first light. Its data so pristine, it's earned Nobel Prizes. Yet they refuse to agree. This isn't just a minor hiccup. It suggests something fundamental is missing from our understanding. Maybe dark energy, the mysterious force accelerating the universe's expansion, isn't constant after all. Maybe gravity behaves differently across vast cosmic distances, or perhaps there's an entirely new ingredient in the cosmic recipe we haven't even dreamed of yet. The stakes couldn't be higher. If the Hubble tension holds, it means our textbooks filled with elegant equations describing the universe's birth, growth, and fate might need a dramatic rewrite. And that's what makes this more than a technical debate. It's a thrilling reminder that the universe still has secrets to reveal, and the biggest discoveries might be hiding in plain sight, written in the stars. The story of the Hubble constant begins not with answers, but with a revolutionary question. Is the universe static, or is it stretching into infinity? In the 1920s, Edwin Hubble, armed with the most powerful telescope of his time, made an observation that shattered centuries of cosmic complacency. By studying distant galaxies, he noticed something strange. The light from these galaxies was subtly shifted toward the red end of the spectrum, a telltale sign they were moving away from us. Not only that, but the farther away a galaxy was, the faster it seemed to be receding. This wasn't random motion, it was a pattern, a cosmic fingerprint revealing that space itself was expanding. Hubble's discovery upended everything. Before this, even Einstein had assumed the universe was unchanging, tweaking his equations to fit that idea, but the evidence was undeniable. The cosmos wasn't static. It had a pulse, a rhythm of expansion. Hubble's initial calculations suggested that for every 3 million light-years a galaxy was from us, it moved away at about 500 kilometers per second. This ratio, the speed of recession per unit distance, became known as the Hubble constant, the number that would define the universe's expansion rate. Yet Hubble's early estimates were rough. His instruments, though groundbreaking for their time, couldn't measure distances with the precision we have today. He wasn't even entirely correct about the implications. For decades, scientists debated whether the expansion would slow down over time, possibly reversing into a big crunch, or continue indefinitely. It wasn't until the late 1990s, when astronomers observed distant supernovae, that they made another jaw-dropping discovery. The universe wasn't just expanding, it was accelerating. This revelation introduced the mysterious force we now call dark energy, and suddenly, the Hubble constant wasn't just a speedometer for the cosmos, it was a key to understanding its ultimate fate. Over the decades, as telescopes grew sharper and techniques more refined, the Hubble constant's value has been tweaked, debated, and refined. From Hubble's original estimate to modern measurements using Cepheid stars and supernovae, each leap in technology brought us closer to pinning down this elusive number. But here's the twist: the better our tools became, the clearer it was that something didn't add up. The Hubble tension isn't just a modern puzzle, it's the culmination of a century's worth of cosmic detective work, where each clue has deepened the mystery rather than solved it. What began as Hubble's bold observation has spiraled into one of cosmology's greatest challenges. The Hubble constant was supposed to be a straightforward measure of the universe's expansion. Instead, it's become a cosmic riddle, reminding us that the more we learn, the more we realize how much we still don't know. To measure the universe's expansion in our cosmic backyard, astronomers rely on celestial milestones, objects so predictable, they're like signposts etched into the fabric of space. Enter Cepheid variable stars, the pulsating heartbeats of the cosmos. These stars brighten and dim with a rhythm so precise, their flickering light reveals their true luminosity. By comparing how bright a Cepheid appears to how bright it actually is, scientists can calculate its distance with remarkable accuracy. It's like judging how far away a lighthouse is by the steady cadence of its beam. But Cepheids are just the first step in a cosmic relay race. To reach even farther, astronomers pass the baton to Type Ia supernova, exploding stars so brilliant they outshine entire galaxies. What makes these supernovae special is their consistency. They all detonate with nearly identical peak brightness, making them perfect, standard candles for measuring mind-boggling distances. Imagine if every firework in the world burst with the exact same intensity. You could gauge how far away one was just by its glow. These methods, refined over decades, form the backbone of our local measurements of the Hubble Constant. Yet they're not without quirks. Cepheids, for instance, need meticulous calibration. Dust drifting between stars can dim their light, tricking us into thinking they're farther away than they are. Supernovae, while dazzling, are rare events you can't predict when or where one will blaze into existence, and both techniques rely on a cosmic distance ladder, where each rung, from nearby stars to distant galaxies, must perfectly align. One misstep and the entire calculation wobbles. Despite these challenges, the precision is staggering. By combining Cepheids and supernovae, scientists have pinned down the local expansion rate to within a few percentage points, a triumph of human ingenuity. But here's the catch. The more precise these measurements become, the harder it is to ignore the glaring mismatch with the CMB's predictions. It's as if two master watchmakers crafted flawless clocks, only to find they tick to different beats. The stakes of this discrepancy are high. If local measurements are correct, it implies something profound. Our universe might not just be expanding, it could be evolving in ways we haven't yet imagined. Every flicker of a Cepheid, every burst of a supernova isn't just a data point. It's a whisper from the cosmos, hinting that there's still so much we don't understand. While local measurements rely on celestial lighthouses in our cosmic neighborhood, the cosmic microwave background takes us back to the very dawn of time itself. This faint glow, often called the echo of the Big Bang, is the oldest light in the universe, a snapshot frozen when the cosmos was just 380,000 years old. Picture it like a photograph from the universe's infancy, capturing the moment when the hot, dense plasma of the early universe cooled enough for atoms to form, releasing light to travel freely for the first time. Today, that light reaches us as a whisper of microwave radiation, bathing the entire cosmos in a nearly uniform glow. The Planck satellite, a marvel of modern astronomy, spent years mapping this primordial light with unprecedented precision. By studying tiny temperature fluctuations in the CMB, patterns no hotter or colder than a few millionths of a degree, scientists can reconstruct the universe's early conditions with astonishing detail. These fluctuations are like cosmic fingerprints, encoding secrets about the universe's composition, shape, and even its destiny. Using Einstein's equations and our understanding of physics, researchers can extrapolate forward from this ancient snapshot to predict how fast the universe should be expanding today. But here's where the plot thickens. Planck's data suggests an expansion rate that's significantly slower than what we measure using nearby stars and galaxies. It's as if we're reading two different chapters of the same book, only to find the storylines don't match. The CMB method relies on the standard model of cosmology, a well-tested framework that includes dark matter, dark energy, and the laws of gravity as we know them. When applied to the early universe, this model predicts a Hubble constant that's about 67 kilometers per second per megaparsec, yet local measurements insist it's closer to 73. This discrepancy isn't just a minor calibration issue. The CMB's predictions come from an era when the universe was unimaginably dense and uniform, governed by physics we thought we understood. If those predictions clash with today's observations, It hints that something fundamental might have changed over cosmic time. Maybe dark energy isn't the constant force we assumed. Perhaps it's been evolving, growing stronger or weaker as the universe ages. Or maybe gravity itself behaves differently across vast stretches of space and time, warping our expectations in ways we haven't yet imagined. What makes the CMB such a formidable puzzle piece is its sheer reliability. Unlike local measurements, which rely on stitching together multiple observational techniques, the CMB offers a single, unified snapshot of the early universe. Its data is so pristine that it's often called the gold standard of cosmology, yet its disagreement with modern expansion rates suggests our cosmic story might be missing a crucial chapter, one that could rewrite our understanding of everything from particle physics to the fate of the cosmos. As we stare into this ancient light, we're not just looking back in time, we're confronting a mystery that challenges the very foundations of how we think the universe works. The gap between these two expansion rates isn't just a minor hiccup, it's a statistically significant chasm that refuses to disappear. We're talking about a difference of roughly 5 to 10%, a number that might sound small until you realize the precision with which cosmologists operate. In most scientific fields, a discrepancy this size would be dismissed as a rounding error. But when it comes to the fundamental laws governing the universe, even a 1% deviation can send shockwaves through our understanding of reality. So, is this just a case of faulty measurements? Could there be hidden errors skewing the results? Scientists have spent years scrutinizing every possible source of mistake. They've checked and rechecked the calibration of telescopes, the algorithms processing the data, even the way light bends through interstellar dust, yet the gap persists. Local measurements, using Cepheids and supernovae, consistently land near 73 kilometers per second per megaparsec. Meanwhile, the cosmic microwave background, our window into the early universe, insists on 67. The odds of this being a random fluke, astronomers calculate it's less than 1 in a million. This isn't noise, it's a signal, screaming that something's missing from our cosmic equation. That leaves us with a far more thrilling possibility. What if our models are wrong? The standard model of cosmology, the framework that's guided our understanding for decades, rests on pillars we've taken for granted: dark energy's constant push, dark matter's invisible grip, gravity's unyielding rules across the cosmos. But what if one of these pillars isn't as solid as we thought? Imagine dark energy isn't a steady force but a dynamic one, growing stronger or weaker over time. Or perhaps dark matter interacts with ordinary matter in ways we haven't accounted for. There's even a radical idea that gravity itself might behave differently on cosmic scales, bending the rules in ways Einstein never predicted. Every time scientists tweak the models to bridge the gap, new problems emerge. Adjust dark energy, and other cosmic predictions fall out of sync. Tweak gravity, and galaxies stop behaving as they should. It's like trying to fix a wobbling table by sawing off one leg only to realize the entire floor is uneven. The Hubble tension isn't just a puzzle, it's a stress test for our entire understanding of the universe, revealing cracks we never knew existed. And that's what makes this moment so electrifying. Science thrives on anomalies, and right now, the Hubble tension is the most tantalizing anomaly in cosmology. Whether it's a subtle error we've overlooked or a gateway to new physics, one thing's certain: the universe is trying to tell us something. The only question is whether we're ready to listen. Some cosmologists argue the Hubble tension isn't just noise, it's the first tremor of a seismic shift in physics. Nobel laureate Adam Rees, whose team first pinpointed the accelerating universe, champions the idea that we're glimpsing dark energy's hidden layers. What if it's not constant, he suggests? What if this mysterious force pushing galaxies apart grows stronger over time, like a spring winding tighter? This theory of evolving dark energy could explain why today's expansion measurements outpace early universe predictions. The push wasn't as strong back then. But other heavyweights urge caution. Wendy Friedman, who spent decades refining cosmic distance measurements, suspects subtle calibration issues might be muddying the waters. Cepheids near massive galaxies behave differently than isolated ones, she points out, like trying to measure footsteps in a crowded room. Sometimes background noise distorts the rhythm. Her team's alternative methods using red giant stars yield expansion rates curiously midway between CMB and supernova results, fueling speculation that both camps might be partially right and partially wrong. Then there's the radical fringe proposing gravity itself needs reinventing. Modified Newtonian dynamics, and advocates like Stacy McGaugh argue Einstein's equations may break down across cosmic scales. Galaxies rotate too fast for their visible matter. What if our gravitational math is fundamentally incomplete? This heresy against dark matter orthodoxy gains traction as new studies reveal peculiar galactic motions unexplained by standard models. The debate splits the astronomy community into three restless factions: the new physics explorers, the meticulous error hunters, and the rulebook rewriters. Telescopes like JWST now join the fray, delivering crisper data on ancient galaxies that somehow look too grown up for their age, another puzzle potentially tied to expansion rate mysteries. With billion-dollar instruments and careers on the line, this isn't academic chess. It's a high-stakes race to either reconcile the numbers or embrace a Copernican-scale revolution in how we comprehend spacetime's stretching fabric. Even the language reflects the tension. Scientists don't call it a problem, but a crisis, the term reserved for moments when paradigms crack. As Princeton's Joe Dunkley puts it, we're either on the brink of Nobel-worthy discovery or the most embarrassing collective oversight in modern astrophysics. The universe, it seems, delights in keeping its deepest secrets just beyond our grasp. Dark energy was supposed to be the universe's simplest cosmic ingredient, a steady, unchanging force woven into the fabric of space itself. But what if we've been wrong about it all along? The Hubble tension has forced scientists to reconsider dark energy's role, and the possibilities are stranger than fiction. Imagine pouring a cup of coffee, only to watch it mysteriously heat up by itself minutes later. That's the kind of bizarre behavior some theorists now suspect dark energy might exhibit, a force that doesn't just push galaxies apart, but one whose strength evolves over cosmic time. Enter phantom dark energy, a hypothetical twist that would make the universe's acceleration not just persistent, but self-reinforcing. Unlike the constant dark energy in our standard models, phantom energy grows stronger as space expands, creating a feedback loop that could eventually tear atoms apart in a catastrophic Big Rip. While this sounds like apocalyptic sci-fi, it's a serious contender to explain why today's expansion measurements outpace early universe predictions. If dark energy was weaker in the past but is now amping up its influence, it could bridge the gap between the CMB's slower expansion rate and our faster local measurements. Then there's the early dark energy hypothesis, which flips the script entirely. This theory suggests dark energy wasn't just a latecomer to the cosmic party, it might have been briefly active during the universe's first few 100,000 years, subtly altering how structures formed before going dormant. Think of it like a ghostly hand that nudged the infant cosmos, leaving fingerprints in the CMB that skew our predictions. Proponents argue this could reconcile the tension without overhauling gravity or inventing new particles, just by tweaking when and how dark energy flexed its influence. But here's the catch: these theories demand radical shifts in our understanding. If dark energy changes over time, it implies an entirely new physics beyond Einstein's cosmological constant, something dynamic, perhaps even tied to undiscovered fields or dimensions. Critics counter that these ideas often feel like patchwork fixes, inventing complexity where there might just be observational errors. Yet with each passing year, as the Hubble tension stubbornly resists resolution, even skeptics admit the allure of reimagining dark energy grows harder to ignore. The irony is palpable. Dark energy was introduced to explain the universe's acceleration, a puzzle in itself. Now, it might be harboring an even deeper secret. Whether it's phantom energy's escalating push, early dark energy's ancient cameo, or something entirely unforeseen, one thing is clear: the mystery of cosmic expansion is far from settled. And the answers, if they come, won't just resolve a number discrepancy. They'll rewrite our story of how the universe lives, breathes, and ultimately shapes its own fate. What if the problem isn't dark energy at all, but gravity itself? For over a century, Einstein's theory of general relativity has been the undisputed rulebook for how gravity shapes the cosmos. But the Hubble tension has some scientists daring to ask, could the rulebook need revisions? Enter modified gravity theories, a radical reimagining of one of physics' most sacred pillars. At the forefront is modified Newtonian dynamics, or MND, a framework that suggests gravity doesn't fade as quickly over distance as Einstein predicted. Instead, it tweaks the equations just enough to explain galaxy rotations without invoking dark matter and, potentially, without the need for dark energy's controversial push. MND's appeal lies in its simplicity. Picture a carousel spinning so fast that riders should fly off, yet they don't. In our universe, galaxies rotate similarly, clinging together despite moving too fast for their visible matter to hold them. Dark matter was invented to explain this grip, but MND offers an elegant alternative. Maybe gravity's pull strengthens slightly in these low-acceleration environments, like an invisible hand tightening its grasp. Proponents argue this could also tweak cosmic expansion rates, bridging the Hubble tension by altering how gravity behaves across vast cosmic scales. But MND faces its own galactic-sized hurdles. While it excels at explaining individual galaxies, it struggles with colossal cosmic structures like galaxy clusters, where dark matter's presence seems undeniable. Worse, it clashes with the breathtaking precision of the cosmic microwave backgrounds, patterns that align perfectly with Einstein's gravity plus dark matter. Critics liken it to fixing a leaky faucet by remodeling the entire house, elegant in theory, but disruptive in practice. Scalar tensor theories take a different approach, proposing gravity isn't just curvature in spacetime, but a dynamic field that evolves with the universe. Imagine gravity as a radio dial, its strength tuning itself over billions of years. These theories allow for subtle variations in gravity's pull across cosmic history, potentially explaining why early and modern expansion rates disagree. But they introduce new complexities, mysterious particles, or extra dimensions that lack concrete evidence. The biggest challenge: these theories live in the shadow of general relativity's flawless track record. Einstein's equations predicted black holes, gravitational waves, even the bending of starlight, all confirmed with astonishing precision. To overturn them requires more than a handful of anomalies. It demands irrefutable proof. Yet the Hubble tension, growing sharper with each observation, keeps the door cracked open. Whether it's Mund tweaks, scalar tensors evolving fields, or something entirely unforeseen, one truth remains. When the universe throws a puzzle this persistent at our fundamental theories, it's often a sign we're on the verge of something extraordinary. The question isn't just whether gravity can be modified, but whether we're brave enough to rewrite the rules. What if the universe isn't the smooth, uniform expanse we've always assumed? Imagine baking a loaf of bread, but instead of a perfectly even rise, you find dense clusters of dough separated by giant air pockets. That's the startling possibility cosmologists are now confronting, an uneven, lumpy cosmos where matter isn't spread evenly but clumps into vast superclusters and sprawling voids stretching billions of light years. This cosmic unevenness isn't just a curiosity, it could be the hidden key to the Hubble tension, warping our measurements of the universe's expansion in ways we never anticipated. Take the local void, a gargantuan emptiness right in our galactic backyard. Spanning over 150 million light-years, this region of sparse matter surrounds the Milky Way like a bubble. Here's the catch: voids expand faster than denser regions, their weaker gravity offering less resistance to dark energy's push. If we're sitting in an underdense pocket of the universe, our local measurements of expansion might be skewed higher, like a speedometer calibrated on a downhill slope. Meanwhile, the cosmic microwave background captures the average expansion rate across the entire universe, smoothing over these lumps and giving a slower, more global value. But voids aren't the only players. The universe is threaded with galaxy filaments, immense threads of matter woven into a cosmic web. These structures create gravitational wells that tug on galaxies, subtly altering their apparent motion. Picture trying to measure the flow of a river while standing in a whirlpool. Your readings might not reflect the true current. Some theorists argue that our position near the edge of the Laniakea supercluster, a colossal filament of 100,000 galaxies, could be distorting our perspective, making nearby galaxies seem to rush away faster than they truly are. The implications are profound. If inhomogeneities, these cosmic bumps and gaps, are significant enough, they could render our local measurements anything but representative. It's like trying to gauge Earth's climate by only recording temperatures in deserts. The Planck satellite's CMB data, by contrast, sees the big picture, averaging over these irregularities. This wouldn't just explain the Hubble tension, it would force us to rethink how we define the expansion rate altogether. Is there even a single true value, or does it vary like a cosmic weather system, faster in voids and slower in dense knots of matter? Skeptics counter that the universe's lumpiness, while real, isn't extreme enough to explain the full discrepancy. Supercomputer simulations of cosmic structure show voids and filaments, but their predicted impact on expansion measurements falls short of the observed gap. Yet others propose an even wilder idea. What if we're in a particularly unusual pocket of space, a statistical outlier on a scale we've barely begun to map? With telescopes like ESA's Euclid mission now charting billions of galaxies in 3D, we're finally gathering the data to test these theories. One thing's certain: the Hubble tension has ripped open a cosmic blind spot. For decades, we've modeled the universe as a smoothly expanding balloon, ignoring the wrinkles in its surface. Now, those wrinkles might hold the answer to one of cosmology's greatest puzzles and remind us that the universe, in all its messy, uneven glory, refuses to conform to our tidy equations. Beneath the radar of even our most powerful telescopes, an invisible sea of particles floods the cosmos neutrinos, the universe's most elusive ghosts. Trillions pass through your body every second, barely interacting with matter, their presence felt more through their absence than their impact. Yet these tiny, nearly massless particles, remnants of the Big Bang's fiery dawn, might hold a hidden influence over the Hubble tension. If their properties differ even slightly from what we've assumed, the ripple effects could rewrite our cosmic playbook. Neutrinos are already cosmic wildcards. Born in the hearts of stars and supernovae, they zip through space at nearly light speed, their three known flavors oscillating in a quantum dance. But here's the twist. The standard model of particle physics pins them as featherlight, with masses so small they're practically an afterthought in cosmological equations. Yet cosmological data hints they might be slightly heavier, or even that undiscovered, sterile neutrinos, entirely invisible to our detectors, could lurk in the shadows. A fraction more mass, an extra flavor, or an unexpected interaction, and these particles could subtly alter how structures formed in the early universe, warping the cosmic microwave background's predictions. Then there's relic radiation, not just the CMB, but other forgotten echoes of creation. Actions, hypothetical particles lighter than neutrinos, could permeate space as a quantum foam, gently tweaking gravity's pull. Or primordial black holes, forged in the universe's first chaotic seconds, might dot the cosmos like invisible anchors, their gravity-bending expansion rates in ways we're only beginning to model. These aren't fringe ideas, they're serious proposals from physicists grappling with the Hubble tension's stubborn grip. The connection to particle physics is profound. At CERN and other labs, experiments hunting for neutrino mass anomalies or dark matter particles now watch cosmology's crisis with bated breath. A mismatch in the Hubble constant might not just be a telescope calibration issue, it could be the first tremor of a particle physics revolution, where the micro and macrocosmos collide. Imagine neutrinos decaying over billions of years, injecting extra energy into the universe's expansion, or actions forming a dynamic lattice that dark energy interacts with, its push varying across epochs. This is where the Hubble tension transcends astronomy. It becomes a detective story spanning the entirety of physics. Every anomalous neutrino detection, every unexplained cosmic structure becomes a potential clue. The universe's expansion rate isn't just a number, it's a mirror reflecting the invisible architecture of reality. And if that mirror is cracked, the fractures might lead us to particles and forces we've never dreamed of, waiting just beyond the edge of our equations. Just when cosmologists thought the Hubble tension couldn't get more perplexing, the James Webb Space Telescope entered the chat, armed with razor-sharp infrared vision and the power to peer deeper into the universe's past than ever before. Scientists hoped JWST's unmatched precision would finally settle the debate, silencing skeptics who blamed measurement errors for the discrepancy. Instead, the telescope's first cosmic distance measurements did the opposite. They deepened the mystery, tightening the knot rather than cutting it. Take the telescope's observations of Cepheid variable stars, those cosmic metronomes we rely on to gauge distances. Previous Hubble Space Telescope data had already established their rhythmic pulses as reliable yardsticks, but JWST infrared eyes cut through interstellar dust that might have skewed past measurements. The result, Cepheid-based expansion rates held firm, confirming the local universe really is expanding faster than early universe models predict. It wasn't a calibration error. It wasn't dust distorting the numbers. The discrepancy was real, and JWST pristine data made it undeniable, but the plot thickens. In 2023, JWST trained its sights on the galaxy MAX 0647, using the gravitational lensing effect of a foreground galaxy cluster to magnify its light. By analyzing time delays between multiple lensed images, researchers derived an independent expansion rate. This method, free from cepheids or supernovae, landed squarely in the middle of the conflicting values. Suddenly, the tension wasn't just two competing numbers, but a full-blown three-way standoff, with each approach backed by JWST gold standard instrumentation. The telescope's most disruptive revelation, however, might be its glimpses of the early universe itself. JWST has spotted galaxies so massive and mature in the cosmic dawn that they defy standard models of cosmic evolution. These cosmic teenagers in the nursery of the young universe suggest structure formed faster than predicted, hinting that gravity or dark matter behaved differently back then. If true, it could mean our extrapolations from the CMB are fundamentally flawed, built on assumptions about the universe's growth that don't hold up under JWST scrutiny. Critics argue that even JWST isn't infallible. Its observations of distant galaxies rely on redshift measurements, which could be contaminated by unexpected dust or exotic physics. But with each new dataset, the telescope narrows the room for error, leaving less space for simple explanations. The telescope was supposed to be the arbiter of the Hubble tension. Instead, it's become the ultimate provocateur, handing scientists a paradox wrapped in pristine data. As one astronomer put it, JWST didn't break cosmology, it showed us where our understanding was already cracked. Now, the race is on to reconcile these findings. Teams are combing through JWST observations, searching for subtle biases or overlooked effects. Others are revisiting theoretical models, testing whether tweaks to dark energy or gravity could explain both the telescope's galactic anomalies and the stubborn expansion rate mismatch. One thing's clear, we're no longer arguing about whether the tension exists. Thanks to JWST, we're staring straight at the cracks in our cosmic framework, forced to ask what monumental truth might lie hidden in the gaps. The Lambda CDM model has been the backbone of cosmology for decades, a set of equations so precise they can predict the universe's structure down to the faintest ripple in the cosmic microwave background. But the Hubble tension isn't just a disagreement over numbers, it's a direct challenge to this foundational framework. At its core, Lambda CDM rests on three pillars: Einstein's cosmological constant, representing dark energy, cold dark matter as the invisible scaffolding for galaxies, and the assumption that gravity follows general relativity's rules without exception. Together, they form a mathematical symphony that's beautifully explained nearly every cosmic observation until now. Consider the cosmic microwave background, the model's crown jewel. Lambda CDM's predictions align so perfectly with the CMB's temperature fluctuations that it feels like unlocking the universe's blueprints. Yet this same model, when extrapolated forward to today's expansion rate, lands stubbornly short of what we observe locally. It's like a watch that keeps perfect time for centuries, only to suddenly start running fast. The discrepancy isn't just embarrassing, it suggests one of Lambda CDM's core assumptions might be fundamentally flawed. Take dark energy, represented by lambda in the equations. The model assumes it's a constant force, unchanging over time and space. But what if it isn't? If dark energy's strength has varied over cosmic history, it could explain why early universe predictions don't match modern measurements. Alternatively, cold dark matter. the CD in the model might interact with ordinary matter in ways we haven't accounted for, subtly altering how structures form and expand. Even more radical, what if Einstein's gravity, the m in the equation, breaks down across vast cosmic distances, bending spacetime in ways we've never observed in our solar system? The stakes couldn't be higher. Lambda CDM isn't just another theory, it's the lens through which we've interpreted everything from galaxy formation to the universe's ultimate fate. If it fails this stress test, the domino effect could reshape cosmology. Some researchers argue the tension is a sign we need new physics, an extra ingredient, like early dark energy or sterile neutrinos, sprinkled into the existing framework. Others believe we're witnessing a Copernican moment, where the entire model might need reinventing from the ground up. The irony is palpable. Lambda CDM was built to explain cosmic acceleration, yet its greatest challenge comes from the very phenomenon it was designed to describe. As debates rage and new data pours in from telescopes like JWST, one thing is clear: cosmology is at a crossroads. Either we're on the verge of a revolutionary discovery, or we're about to learn just how resilient or fragile our understanding of the universe truly is. What if our universe isn't alone but just one bubble in a frothing cosmic sea? The Hubble tension has pushed scientists to the edge of known physics, and some are daring to ask, could the answer lie beyond our cosmic horizon? Enter multiverse theories, where the very laws of nature might shift from one pocket of reality to another. Imagine two adjacent soap bubbles, each with slightly different surface tension. One expands faster, the other slower. If our universe is one such bubble, its unique expansion rate could simply be a local quirk, with other universes out there obeying entirely different rules. This isn't just wild speculation. Eternal inflation, a leading theory of cosmic origins, suggests our Big Bang might have been one of countless others, each spawning a universe with randomly determined constants. In this view, the Hubble tension could be a fingerprint of our bubble's peculiar physics: dark energy slightly stronger here, gravity subtly weaker there, a cosmic accident frozen into the fabric of our existence. The tantalizing part: if true, it would mean the true expansion rate doesn't exist. Every universe dances to its own rhythm, and ours just happens to be out of sync with our expectations. But how do we separate science from science fiction? While multiverses are mathematically plausible in string theory and quantum cosmology, they're notoriously hard to test. Some physicists propose hunting for bruises in the cosmic microwave background, anomalous patterns where our universe might have collided with a neighboring bubble. Others suggest subtle variations in fundamental constants across space could hint at a larger, fragmented reality. So far, no smoking gun has emerged, leaving the multiverse camp in a frustrating limbo, compelling in theory, elusive in practice. Skeptics argue this is a cop-out, an untestable idea that explains everything and therefore nothing. Yet the Hubble tension's persistence keeps the door ajar. If all conventional fixes fail, might we need to confront the radical notion that our universe isn't the standard but the outlier? Whether a multiverse exists or not, the mere possibility forces us to rethink the most basic question of all: is physics as we know it the rule, or just a fluke in an unfathomably vast cosmic tapestry? The answer, if it comes, might rewrite not just our textbooks, but our place in reality itself. Measuring the universe's expansion sounds straightforward until you realize no two telescopes see the cosmos exactly the same way. Hubble and Gaia, two of astronomy's most powerful observatories, have spent years collecting data on the same stars, yet their measurements sometimes clash like rival cartographers mapping the same continent with different rulers. This isn't just a minor technical hiccup, it's a calibration crisis that fuels the Hubble tension, forcing scientists to ask, are we comparing cosmic apples to oranges? Take Cepheid variable stars, those critical mile markers for gauging distances. Hubble observes them in visible light, its sharp eyes resolving individual stars even in crowded galactic cores. But Gaia, orbiting farther from Earth, scans the sky in infrared, piercing dust clouds that obscure Hubble's view. In theory, their measurements should align. In practice, subtle discrepancies emerge. Hubble might see a Cepheid's pulse slightly brighter or dimmer than Gaia records differences of mere percentages, but enough to nudge the expansion rate up or down. It's like two chefs using identical recipes but different measuring cups. The cake might rise unevenly, and no one's sure whose tools are off. The stakes escalate when we consider parallax, the gold standard for cosmic distances. As Earth orbits the Sun, nearby stars appear to shift against the backdrop of distant galaxies, and measuring this tiny wobble reveals their distance with precision. Gaia's billion-pixel camera excels at this, tracking stars with micrometric accuracy, but here's the catch. Gaia's parallax measurements for some Cepheids suggest they're closer, and thus intrinsically dimmer, than Hubble's calculations imply. If true, it would mean these stars are poorer standard candles, throwing off the entire cosmic distance ladder. Skeptics argue these discrepancies stem from calibration gremlins. Hubble's mirrors, though legendary, suffer from focus breathing, tiny distortions as temperatures shift in orbit. Gaia's detectors, while ultra-precise, struggle with crowded star fields where light from neighboring stars bleeds together. Even the choice of filters' specific wavelengths each telescope uses can tint the data. One team's correction for interstellar dust might be another team's oversight, leaving the community in a tug-of-war over whose adjustments are justified. Yet the plot thickens. In 2021, astronomers cross-checked Hubble and Gaia's data using a third method: masers, natural lasers in star-forming regions that emit radio waves with razor-sharp precision. These maser-based distances landed somewhere between the two telescopes' estimates, deepening the mystery rather than solving it. The unsettling conclusion: there may be no single right calibration, just layers of uncertainty woven into every measurement, each reflecting the unique biases and blind spots of its instrument. This calibration conflict isn't just academic nitpicking. If even part of the Hubble tension stems from mismatched tools, it could mean the universe's expansion rate is more consistent than we think, hidden beneath a fog of technical noise. Alternatively, if the discrepancies reveal deeper flaws in how we measure cosmic distances, the implications ripple far beyond the tension itself. Every textbook value, from the age of the universe to the scale of galaxy clusters, hinges on these delicate calibrations. The real lesson here isn't just about conflicting data. It's a humbling reminder that in cosmology, the tools we trust to reveal truth might also obscure it. The cosmology community isn't just quietly crunching numbers, it's a battleground of clashing egos, heated debates, and conference showdowns where careers hang in the balance. Picture a packed auditorium at the International Astronomical Union's General Assembly, where two Nobel laureates stand toe-to-toe over a microphone. One holds up a graph from the latest JWST data, arguing it confirms the local expansion rate beyond doubt. The other counters with a Planck satellite map, declaring any deviation from the CMB's predictions is pure statistical noise. The moderator, caught between them, jokes about needing a referee's whistle. These clashes aren't confined to polite panel discussions. At a 2022 conference in Kyoto, a team presenting evidence for early dark energy faced a barrage of interruptions not from skeptics, but from an astronomer who'd spent 30 years calibrating Cepheid stars. "Your model breaks the distance ladder," he argued, slamming his laptop shut mid-presentation. The room erupted into side conversations, with graduate students exchanging wide-eyed glances as senior researchers formed impromptu huddles in the hallway, scribbling equations on napkins. The human drama behind the Hubble tension is as compelling as the science itself. There's the young postdoc who discovered her supernova data was being dismissed by a prominent professor until she proved his team had overlooked a key dust correction. Or the veteran cosmologist who publicly bet his entire book advance that the tension would vanish within 5 years, only to double down when JWST's data came in. These aren't just academic spats, they're high-stakes battles over how we define reality itself, fought with PowerPoint slides and margin of error calculations instead of swords. What fuels these clashes isn't just pride, it's the terrifying possibility that entire lifetimes of work might be built on flawed assumptions. A theorist who's spent decades refining dark energy models isn't just defending a paper, they're defending their legacy. Meanwhile, the upstarts armed with new data smell blood in the water, convinced they're witnessing a paradigm shift. The conferences become pressure cookers, where a single anomalous graph can turn a colleague into a rival overnight. Yet beneath the drama lies a shared desperation to crack the mystery before the next generation of telescopes renders all their arguments obsolete. The debates rage on, unresolved. In one corner, the systematics camp pores over calibration spreadsheets, convinced the answer lies in better data cleaning. In another, the new physics crowd sketches wild theories on whiteboards, fueled by late-night espresso. And in the middle, the moderates whisper about compromise. Maybe the truth lies somewhere between. But one thing's certain, until the universe coughs up its secrets, these conferences will keep serving up fireworks, proving science at its most contentious is also science at its most alive. Supercomputer simulations have long been the proving grounds for our cosmic theories' digital universes, where we can tweak the laws of physics with a keystroke and watch galaxies evolve in fast forward. These virtual cosmos are built on the bedrock of lambda CDM, the same model that predicts the cosmic microwave background with uncanny precision. But when we pit these simulations against the real universe, especially in the face of the Hubble tension, the cracks start to show. Imagine building a flawless scale model of Earth, only to discover the real planet has an extra continent no one told you about. That's the unsettling gap between simulations and reality when it comes to cosmic expansion. Take the illustrious TNG project, one of the most ambitious universe simulations ever run. Feed it the CMB's initial conditions, let it churn for billions of virtual years, and out pops a cosmos teeming with galaxies that look eerily like our own. Yet when researchers compare its predicted expansion rate to today's observations, the numbers drift apart like two ships losing radio contact. The simulation's Hubble Constant, based squarely on lambda CDM's rules, lands closer to the CMB's slower value, not the faster rate we measure locally. It's as if the digital universe obeys the textbook perfectly, while the real one plays by its own hidden rules. The discrepancies get stranger when we zoom in on cosmic structures. Simulations predict how galaxy clusters should grow and merge over time, their gravitational dances choreographed by dark matter and dark energy. But real-world observations reveal clusters that are oddly puffier, less densely packed than the models suggest. Some galaxies move faster than expected, as if tugged by invisible strings. These anomalies hint that gravity might not work exactly as programmed into the simulations, or that dark matter interacts in ways we haven't accounted for. It's like watching a ballet where half the dancers ignore the steps, forcing us to question whether we've misheard the music. Then there's the timing problem. Simulations like UCHU or Millennium trace the universe's evolution from infancy to today, marking when massive galaxies should first ignite with stars. Yet JWST keeps finding fully formed galaxies in the cosmic dawn, mature cities where the simulations expect sleepy villages. If structures formed faster than lambda CDM predicts, it could mean the early universe expanded differently, throwing off our backward calculations of today's expansion rate. Picture reconstructing a train's speed by studying its wreckage, only to realize it had an extra engine no one told you about. The most provocative mismatches come from the universe's largest scales. Simulations generate cosmic webs, vast filaments of dark matter, where galaxies cluster like dew on a spider's silk. But recent 3D maps of millions of galaxies reveal a web that's subtly inconsistent. Some voids are emptier, some filaments more twisted, as if an unseen hand tweaked the simulation's parameters midway through. Could this be the fingerprint of dynamic dark energy? A sign that gravity weakens over cosmic distances, or proof that we're missing an entire ingredient in our virtual recipes? Critics argue simulations are only as good as their assumptions, garbage in, garbage out. Maybe we've underestimated how ordinary matter and dark matter interact, or overlooked quantum effects that ripple across billions of light years. Others see these gaps as clues to something grander. Every mismatch is a breadcrumb leading beyond lambda CDM, hinting at physics too exotic for our current codes to simulate. After all, the universe doesn't owe us simplicity. Its greatest secrets might be hidden in the spaces between our models and reality, waiting to rewrite not just cosmology's rules, but the very code we use to simulate them. The Hubble tension may be the most frustrating puzzle in modern cosmology, but a new generation of telescopes is gearing up to crack it wide open. Leading the charge is Nancy Grace Roman Space Telescope, set to launch in the next few years. Unlike its predecessors, Roman won't just peer at individual stars or galaxies, it'll conduct a sweeping cosmic census, mapping millions of supernovae and galaxies across unimaginable distances. Its secret weapon, a field of view 100 times wider than Hubble's, allowing it to spot thousands of Type Ia supernovae in distant galaxies. These stellar explosions are our most reliable yardsticks for measuring cosmic expansion, but current samples are frustratingly small. Roman's avalanche of data could finally reveal whether local measurements have been skewed by statistical flukes, or if the discrepancy with the CMB is etched into the fabric of reality itself. Meanwhile, ESA's Euclid spacecraft is taking a radically different approach. Instead of hunting supernovae, Euclid will chart the invisible skeleton of the cosmos, the dark matter web that shapes how galaxies cluster and move. By measuring subtle distortions in the light of billions of galaxies, a phenomenon called weak gravitational lensing, Euclid can trace how cosmic structures have grown over time. This growth rate is exquisitely sensitive to the universe's expansion history. If dark energy has been changing strength, or if gravity behaves oddly on large scales, Euclid's 3D maps of the dark universe should expose it. The telescope's infrared eyes will also peer back to when the universe was just 3 billion years old, capturing snapshots of expansion during an era barely probed by current instruments. Then there's LSST, the legacy survey of space and time, set to revolutionize astronomy from its perch in Chile. Every few nights, this ground-based behemoth will scan the entire southern sky, spotting anything that moves or flickers, including millions of distant supernovae and quasars. But its real power lies in sheer volume. By catching so many cosmic mileposts across different epochs, LSST could reveal whether the expansion rate varies not just between early and modern times, but subtly across different regions of space. Imagine discovering the universe expands faster in one direction than another, a jaw-dropping possibility that could upend our assumption of cosmic uniformity. These missions share a common goal: to attack the Hubble tension from multiple angles, leaving no hiding place for errors or overlooked physics. Roman supernova Hall could confirm or demolish local measurements. Euclid's dark matter maps might expose flaws in our gravity equations. LSST All-Sky Patrol could uncover cosmic irregularities we never imagined. Together, they form the most ambitious assault yet on cosmology's biggest mystery. The next decade won't just bring better data, it might force us to rewrite the rules of the cosmos, and when that happens, the Hubble tension won't be a crisis anymore. It'll be the clue that led us to something far deeper, a universe stranger, richer, and more astonishing than we ever dreamed. History has a way of humbling even the most confident scientific minds. Just over a century ago, astronomers believed the Milky Way was the entire universe until Edwin Hubble proved galaxies existed beyond our own, instantly expanding the known cosmos 100,000-fold. Before that, Newton's clockwork universe seemed unshakable until Einstein showed space and time were fluid, bending under gravity's weight. And who could forget the geocentric model, where Earth proudly sat at creation's center for millennia before Copernicus sent it spinning around the sun. Time and again, cosmology has reminded us, what we call laws are often just placeholders for deeper truths we haven't uncovered yet. The Hubble tension forces us to confront this legacy of upheaval. Right now, physicists are split between two uncomfortable possibilities. Either we've made subtle errors in measuring the universe's expansion, a sobering reminder of human fallibility, or we're standing at the brink of another Copernican scale revolution. Imagine future textbooks describing dark energy not as a constant, but as a dynamic force that ebbs and flows across cosmic time, or gravity not as Einstein envisioned, but as a law that subtly rewrites itself across vast distances. These aren't just tweaks, they're paradigm quakes that could redefine reality's rulebook. Consider how drastically our cosmic self-image has shifted in living memory. In the 1990s, astronomers were still debating whether the universe's expansion would slow down, leading to a Big Crunch collapse. Then supernova observations revealed the opposite. Space was accelerating apart, propelled by some unknown dark energy. Overnight, our cosmic endpoint went from fiery collapse to icy dissipation. If such a foundational idea could flip so recently, why couldn't the Hubble tension be the next seismic shift? Science doesn't progress in straight lines. It lurches forward when anomalies like this refuse to be ignored. There's a deeper lesson here about the nature of discovery. For all our equations and supercomputers, the universe remains stubbornly opaque, revealing only fragments of its grand design. the Hubble tension might feel like frustration, a glitch in our otherwise elegant models, but history suggests these are precisely the moments when science leaps ahead. When Mercury's orbit didn't match Newton's predictions, it wasn't a failure, it was a clue pointing toward relativity. When the CMB's temperature variations first surfaced, they seemed like noise, until they became the blueprint for cosmic structure. Could today's expansion rate mismatch be tomorrow's Nobel Prize-winning insight? This isn't just about astronomy, it's about epistemology. How do we know what we know? The Hubble tension exposes the fragile scaffolding of human knowledge, where even our most cherished theories are provisional, always one observation away from revision. That's not weakness, it's science's greatest strength. Every anomaly is an invitation to look deeper, to question harder, to admit we might not have the final answer. After all, if the universe were simple enough for us to fully understand, we probably wouldn't be complex enough to comprehend it. The real wonder isn't that we're wrong sometimes, it's that we've gotten so much right, and that the cosmos keeps trusting us with its next impossible riddle. Every time the Hubble tension makes headlines, clickbait declarations scream, "Einstein proven wrong," or "Physics in crisis," but the reality is far more nuanced. Relativity isn't crumbling, it's being stress-tested in ways that could ultimately strengthen it. Imagine a bridge engineered to hold 10 tons suddenly bearing 11. The creaks and groans don't mean the bridge is flawed, they're clues to where reinforcements might be needed. Similarly, the discrepancy in cosmic expansion rates isn't a demolition crew for Einstein's theories, but a spotlight on where our understanding might need fine-tuning. The media's obsession with overturning science often misses a crucial point. Good theories evolve. Newton's laws didn't become useless when relativity emerged. They became a special case within a broader framework. Today's tension could follow the same path. General relativity has survived a century of brutal tests, from predicting black holes to explaining the precise orbit of Mercury. The Hubble tension might not break it, but could reveal where new layers like quantum gravity or exotic dark energy need to be woven into the existing tapestry. Consider how these headlines distort the scientific process. When researchers say, "We might need new physics," they're not confessing ignorance, but celebrating science's self-correcting nature. The tension isn't a flaw, it's the system working as designed. Imagine if every discrepancy in your car's speedometer led to headlines declaring automotive engineering collapses. Instead of mechanics checking the alignment, cosmology operates the same way. Anomalies aren't failures, but invitations to dig deeper. What's often lost in sensationalism is the scale of the challenge. Measuring the universe's expansion is like trying to clock the speed of a growing balloon while standing on its surface. Every method has blind spots. Local measurements might be skewed by cosmic voids, while CMB data could hide wrinkles from the universe's infancy. Dismissing relativity because of this tension is like rejecting germ theory because one lab culture got contaminated. The scientific method thrives on these tensions, using them to separate true breakthroughs from measurement noise. One of the most damaging myths propagated by oversimplified media is the idea of finished science, the notion that theories are complete rather than continually refined. Relativity itself was born from a tension, the mismatch between Newtonian predictions and the behavior of light. If Einstein had taken the headline, Newton was wrong. At face value, he might have discarded the baby with the bathwater. Today's cosmologists face the same dilemma. The Hubble tension could hint at undiscovered physics, but shouting "crisis" risks overshadowing the meticulous work needed to distinguish real anomalies from observational artifacts. The truth is, relativity isn't a sacred text but a living framework, one that's repeatedly absorbed shocks without shattering. Even if the Hubble tension demands new physics, it's far more likely to nestle within relativity's flexible equations than to obliterate them. After all, Einstein's genius wasn't in being infallible, but in building a theory robust enough to guide us even when it's incomplete. Until telescopes like Roman or Euclid deliver irrefutable evidence, the real story isn't Einstein versus the data, but how Einstein's legacy is helping us ask better questions. And that's a headline worth waiting for. When the numbers don't add up and the universe refuses to follow the script, it's no surprise that some voices on the fringe start whispering about cover-ups. Scientists are hiding the truth, they claim. The Hubble tension isn't a mystery, it's a lie. These conspiracy theories often paint a picture of shadowy elites suppressing dissent, deliberately obscuring flaws in the Big Bang theory to protect their funding or reputations. But let's pull back the curtain on how science actually works, because the reality is far messier, more transparent, and ultimately more fascinating than any conspiracy could dream up. Take the peer review process, the backbone of scientific credibility. When a team submits a paper claiming to solve the Hubble tension, whether by tweaking dark energy or overhauling gravity, it doesn't vanish into some academic black hole. It gets blasted with scrutiny from rivals, skeptics, and even junior researchers hungry to make their mark. Every equation is checked, every data point questioned. Remember, the team that suggested early dark energy might bridge the gap. Their work was torn apart in online forums before it even reached publication, with astronomers worldwide dissecting their assumptions in real time. That's not suppression, it's the sound of science self-correcting, loudly and publicly. Then there's the myth of unanimous consensus. Conspiracy theorists love to claim scientists march in lockstep, but spend 5 minutes at any cosmology conference, and you'll witness a blood sport of competing ideas. Nobel laureates spar with grad students over coffee breaks. Prestigious journals publish papers with titles like "Why Lambda CDM Must Be Wrong." The Hubble tension itself is proof of this chaos. Researchers aren't hiding the discrepancy. They're obsessed with it, racing to publish the next big clue. If there's a conspiracy, it's the worst organized one in history, with its members constantly betraying the party line in pursuit of tenure or a flashy headline. The most ironic twist, many of the Hubble tension's loudest critics inside academia, the ones proposing radical fixes, started as outsiders. Take the physicists pushing modified gravity theories. A decade ago, they were dismissed as rebels. Now their ideas get serious airtime because the data forced the community to listen. Science isn't a cathedral guarded by high priests. It's a raucous marketplace where the best evidence wins, even if it takes years or centuries to settle the debate. So why do the conspiracy theories persist? Partly because the universe is stranger than fiction, and it's easier to blame human deceit than accept how much we still don't know. But mostly because the real story of flawed, competitive, brilliant humans piecing together cosmic truths through endless trial and error isn't as thrilling as a Hollywood plot. The Hubble tension isn't proof of a lie. It's proof that science, at its best, is a spotlight shone directly on its own uncertainties, inviting the world to watch as it stumbles toward the light. In the race to crack the Hubble tension, there's more at stake than just scientific glory. There's the shimmering possibility of a Nobel Prize waiting for whoever untangles this cosmic knot. History shows that paradigm-shifting discoveries about the universe's expansion tend to catch the Nobel Committee's eye. Just look at '98, when Saul Perlmutter, Brian Schmidt, and Adam Rees split the prize for proving the universe's acceleration, a revelation that hinged on measuring the Hubble constant. Now, with the tension threatening to upend cosmology again, the stakes feel even higher. So who's in the running to take home science's top honor? Adam Rees, already a Nobel laureate, remains a frontrunner. His team's relentless refinement of local measurements using everything from Cepheid stars to red giants has only deepened the discrepancy with early universe predictions. If he can prove the mismatch stems from new physics rather than measurement errors, it could cement his legacy with a rare second prize, but he's not working in a vacuum. Wendy Friedman, another heavyweight, has championed alternative distance ladders using red giant stars, landing on an expansion rate that intriguingly splits the difference between conflicting values. Her meticulous approach could sway the committee if she proves systemic errors have skewed past results. Then there's the dark energy disruptors. Mark Kamienkowski, a theoretical physicist at Johns Hopkins, has floated radical ideas like early dark energy, a brief surge of repulsive force in the universe's infancy that could reconcile the tension. If future data from JWST or Euclid validates his models, it would revolutionize our understanding of cosmic acceleration. Similarly, Lucas Lombrizer's work on scalar tensor gravity modifications, which tweak Einstein's equations just enough to explain the discrepancy, has gained traction. The Nobel Committee loves elegant theoretical leaps and either could ride that wave to Stockholm, but don't count out the instrument builders. Nobels often reward those who develop the tools that make breakthroughs possible. Astronomers behind JWST CRISPR-Cepheid measurements, or IS's Euclid team, whose 3D dark matter maps might expose hidden flaws in lambda CDM, could share the spotlight. Even dark horse contenders like Stacy McGaugh, who spent decades challenging dark matter orthodoxy with modified gravity theories, could vault into contention if the tension forces a fundamental rewrite of astrophysics. The wild card, collaboration. Modern cosmology is a team sport, and the Nobel's strict three-person limit feels increasingly out of sync with today's mega collaborations. Some speculate the committee might bend tradition, honoring entire missions like Planck or JWST. But one thing's certain, solving the Hubble tension won't just earn a medal, it'll redefine our place in the cosmos. Whether the answer comes from a lone genius or 1,000 minds crunching data, the winner won't just take home a prize, they'll rewrite the universe's story. You don't need a PhD or a billion-dollar telescope to help solve the Hubble tension, just a curious mind and an internet connection. Across the globe, ordinary people are making real contributions to cosmology through citizen science projects, turning their living rooms into frontier labs for cosmic discovery. Platforms like Zooniverse host initiatives where volunteers sift through telescope images, classifying galaxies or hunting for supernovae, tasks that even the most advanced algorithms still struggle with. Imagine scrolling through real data from the Hubble Space Telescope, spotting a flickering star that could be the next critical clue in the expansion rate debate. That's not science fiction, it's happening right now, and it's rewriting who gets to participate in humanity's greatest detective story. One standout project is Supernova Hunters, where amateur astronomers scour images for telltale flashes of dying stars. Type I a supernova, those cosmic mile markers, are notoriously finicky. Their brightness must be measured with pinpoint accuracy to calculate distances. But with thousands of galaxies to monitor, Professional researchers rely on eagle-eyed volunteers to flag potential candidates. In 2021, a retired schoolteacher in Germany spotted a supernova later confirmed as one of the most distant ever recorded, proving that breakthroughs don't always come from ivory towers. These discoveries feed directly into the Hubble tension debate, refining the local expansion rate one explosion at a time. Then there's CRED, a project that enlists gamers to map cosmic dust, a sneaky culprit that can distort starlight and throw off distance measurements. By playing an interactive game, users trace dust filaments in galaxy images, helping scientists calibrate observations of Cepheid variables and other celestial yardsticks. It's like solving a puzzle where every piece cleaned of dust brings us closer to the true expansion rate. Even high school students have contributed, their collective work published in peer-reviewed journals alongside veteran astronomers. For those who prefer number crunching, CosmoQuest lets volunteers analyze data from NASA's IS telescope, measuring galaxy shapes to probe dark energy's influence on cosmic growth. The project's founder, Dr. Pamela Gay, often says, "The universe is too big for any one team to decode." She's right. When thousands of eyes scrutinize the same data, patterns emerge that even supercomputers might miss. One volunteer, a graphic designer with no formal astronomy training, helped identify a rare galaxy cluster whose peculiar motion could hint at modified gravity, adding fuel to the Hubble tension fire. What's revolutionary about these projects isn't just the science, it's the democratization of discovery. The Hubble tension isn't just a puzzle for elites in lab coats, it's a collective challenge where a teenager in Tokyo or a retiree in Buenos Aires might stumble on the key. Every classified galaxy, every logged supernova, tightens the noose around this cosmic mystery. So the next time you gaze at the night sky, remember, you might not need a telescope to change astronomy. Sometimes, all it takes is curiosity, a laptop, and the willingness to dive into the unknown alongside the pros. Who knows? The next critical clue in the universe's greatest riddle could come from you. The Hubble tension might just be the universe's greatest prank, a cosmic joke played on the scientists who thought they had it all figured out. After decades of meticulous observation, cutting-edge technology, and Nobel Prize-winning breakthroughs, we're left staring at two numbers that refuse to agree. It's as if the cosmos is grinning at us, dangling a puzzle just out of reach, whispering, "You think you know me, but here's the beautiful part, this isn't a failure of science." It's science at its best, reminder that the universe is under no obligation to make sense to us. What if the tension isn't a problem to solve but a doorway? Every great leap in understanding from Galileo's telescope to Einstein's relativity began with an anomaly that refused to disappear. The discrepancy in the expansion rate could be the first tremor of a revolution, a sign that dark energy isn't what we thought, that gravity has hidden rules, or that our universe is stranger than we dared imagine. Or maybe it's simpler, a subtle error in our measurements, a cosmic mirage we'll one day laugh about. Either way, the tension isn't a dead end. It's an invitation to look deeper, to question harder, to stay humble in the face of the unknown. So where does that leave us? Not with answers, but with something even more valuable, better questions. The Hubble tension has already reshaped cosmology, forcing us to rethink assumptions we didn't even realize we'd made. It's proof that the universe still has secrets, and that the next great discovery might be hiding in the gap between two numbers. Whether it's a flaw in our tools or a flaw in our theories, one thing's certain, the cosmos isn't done surprising us. So keep looking up, stay curious, because the most exciting chapters of this story haven't been written yet. and you're here to witness them unfold. If you want to be the first to know when the next breakthrough cracks this cosmic case, hit subscribe and ring the bell. The universe might be trolling us for now, but the punchline, it's going to be unforgettable. So after all this, is the Hubble tension just a cosmic speed bump, or the tip of a universe-sized iceberg? Maybe the real question isn't how fast space is stretching, but whether we've been reading the cosmic rulebook all wrong. Next time, we're diving into an even bigger mystery. If dark matter is the universe's invisible scaffolding, why can't we prove it exists? Spoiler alert, the answer might shake physics to its core. Drop your wildest theories in the comments. Do you think we're missing a hidden dimension, a glitch in gravity? Or is the universe just messing with us? Smash that subscribe button so you don't miss the next mind-bending episode. And remember, in a cosmos where even the laws of physics might be up for debate, the only wrong answer is not asking questions. See you in the next paradox. Cue explosion of confused emoji asteroids.